Multi-agent coding fails in a very annoying way. Every candidate looks correct until they meet. I have watched two coding agents both pass their local tests, both produce clean pull requests, and then break the main branch together. One renamed a response field, the other added a caller using the old field based on a stale checkout. No conflict markers, no red tests inside either worktree. The failure only existed in composition. That is the point of this episode. Parallel agents are not done when they pass alone. They are done when their work composes on an integration branch. The naive setup is simple. Give several agents tasks, let them edit the repo, run tests, and review the winners. It feels fast. It is also where evidence gets muddied. If agents share a branch, you cannot tell who changed what. If they share a worktree, one agent may accidentally depend on another agent's half-finished change. If you only review natural language summaries, you miss file drift. And if you wait for the normal merge queue, you discover composition failures after you have already paid for expensive verification. The core problem is not just isolation. Episode 4 covered isolated worktrees. The missing half is proving that isolated results can be combined. The pattern is opinionated. One task, one branch, one worktree, one verdict. Each candidate gets a task packet that says what it may touch and what success means. Before you run the expensive verification, you inspect the real git diff against the base and enforce the allowed scope. Not the agent's report, not a plan, the diff. Candidates that pass scope and local checks become integration candidates. Then you create an integration branch, cherry-pick the selected candidate commits, and run full system verification there. This separates two questions. Did the agent stay inside the task boundary? And does the combined system still work? Mechanically, start by issuing a task packet with task ID, worktree, branch, allowed scope, and success checks. The agent works only in that worktree and leaves checkpoint commits, reproduce, fix, tests, and candidate. When it claims done, compute get diff name only from base to head. If any file is outside allowed scope, return a scope violation with unexpected files. Do this before verification, because there is no point spending 10 minutes testing a candidate that touched the billing module during a styling task. If scope passes, run its success checks. Mark one verdict. For integration, create a fresh branch from the current base, cherry-pick candidate commits, then run full system checks. If base is stale is true, rebase first and retest. Imagine two coding agents. Agent A changes an API response from username to display name and updates the backend tests. Agent B adds a dashboard widget and was allowed to touch only the front-end widget folder. Each has its own branch and worktree. Agent B passes its local component tests because its fixtures still use username. The scope gate catches no drift, so both are candidates. On the integration branch, you cherry-pick A, then B. There may be no textual conflict, but the combined type check fails because the widget expects the old field. Now you hand an integration agent a conflict packet, intent from candidate A, intent from candidate B, and required combined behavior. Its job is not to silence errors. This pattern is not magic. If allowed scope is too broad, the scope gate becomes decorative. If it is too narrow, agents bounce on legitimate cross-cutting work. Some conflicts are semantic. Two candidates change caching assumptions, and no type checker complains. Your full system checks must match the risk of the change. Another failure is letting the integration agent invent a third requirement while fixing a conflict. That is why the conflict packet carries both intents and required combined behavior. Also, keep failed work trees until evidence is preserved. I have seen teams delete the only reproduction of a failure because the automation cleaned up too aggressively. This sits in the middle of loop engineering's pattern tier. Work trees give you isolation but not composition. Verification budgets keep you from running the whole suite on every messy draft. State tracking records the base commit, verdict, unexpected files, and checkpoint hashes. The orchestrator, not the agent, owns the verdict. That distinction matters. Agents can propose, repair, and explain, but the loop decides when evidence is sufficient. At fleet scale, integration branches become the pressure valve. You can run many narrow attempts in parallel, then only promote the candidates that survive scope gates, stale base checks, and combined verification. Try this on your own automation in 10 minutes. Pick one small repo and one safe task. Write a task packet with task ID, branch, worktree, allowed scope, and success checks. Create a worktree and make any tiny change, even manually. Commit it as candidate. Now run git diff name only from where base commit to the candidate. Compare every changed file to allowed scope. If one file is outside the list, record scope violation and unexpected files. If it passes, create an integration branch from base, cherry-pick the candidate, and run a broader check than the local one. The point is not the tool. The point is making composition an explicit stage. 3 beats to keep. First, in multi-agent coding, enforce scope from the real git diff before you spend on verification. Second, individually green candidates can fail when combined, so prove composition on an integration branch with full system checks. Third, old base test results are stale evidence. If the base moved, rebase or regenerate the verdict. My bias is strict here because loose evidence creates confident breakage. This is episode 30 of Loop Engineering, a daily series on building agent loops that finish, verify, and stop. Tomorrow we keep adding patterns that survive contact with production.